Hi guys, it's Devin. Welcome to week 6. I'm so excited to do some more CAD stuff with you guys. I know there were some frustrations in the last activity, and that was to be expected, but I'm glad it seems like a number of you really have gotten the hang of it. It is a big jump, as I mentioned, from Tinkercad and 123 Design, but man, does it have more capabilities. It's amazing. So this is Onshape's a free software, and it has almost all of the tools that I had access to when I was at Tufts with another software called SolidWorks, which you need to pay for licenses to have, and they're not cheap. So to have all this free and increasing the access to CAD is awesome. And this week we're talking about why we do it. What are the uses of CAD besides just having to do these assignments? There's a lot of cool stuff that we can do with CAD. I mean, it's as big as being integral to architecture and architectural design and the crazy intricacies and the kind of time and energy that goes into those models. But now it's also as simple as just doing 3D prints. And that's why it's so cool that it has reached this amazing spectrum, and to have a software like Onshape that is free, that you can do some very simple making and have going in your makerspace is amazing. And I hope it's a skill you guys are able to take with you into your classrooms and show some of your students, because it's very empowering. For my part, it was the first time I really felt creative, and not creative, but artistic. I was never good at drawing or painting or anything like that, but when I started freshman year and started doing CAD work, you were given tools and actually able to take something from this vision in your head to the screen, and that was amazing. My first big project with it was to make a piggy bank, and the only instructions was it had to have a certain size slot and a place to put the quarters in, and that was it. And I made R2D2, and it was such a fun project. If I get the chance, I'll try to post it this week as my post if I can dig it up and find it somewhere. But it's so much fun when you get the hang of the tools. It's certainly frustrating when you can't figure out exactly what you want to do, but hopefully you can use us as a resource. I know for myself, you can always reach out to me. I can do screen shares pretty easily now and can give you some one-on-one help, because it's not easy, and we don't want you guys to get frustrated. When you reach that point, I hope you guys can just take a step away, de-stress, reach out to me, get some help, do some searches on the internet. It's really hard to just brute force your way through problems in CAD, and really frustrating, and I don't want you guys to be frustrated. You have all this other stuff happening in your lives. I don't want these assignments to add anxiety to any of that. So we're going to go through some of the examples of where CAD is used. The first couple will be in these slides. They're very based on modeling and kind of analysis work. And then very conveniently, I had to do some CAD work for the museum this week. And that really actually tackles a lot of the things where I think CAD is useful. So one of the main uses for CAD that Onshape does not have that other more expensive CAD softwares have is finite element analysis, FEA. So what you can see here is a part that you can imagine being made in a CAD software, right? You could see yourself maybe drawing an outline and then extruding it all the way through, and then getting a top view and kind of cutting away those holes in those different parts. But what this does is then takes that and says, okay, we're going to put these arrows here. You guys can see we're going to apply force. Whatever this part is doing, clearly they're expecting it to get a lot of force at those end couplings and not too much in the center. And then it just runs an analysis based on the material it is. It looks at the thicknesses, the lengths of things. It's incredible what some of these softwares can do. Sometimes it takes a while. If you have a complicated shape, it's not unheard of for it to take an hour. For a really complicated shape, I've heard of people having to leave it overnight for the computer to run all of those calculations. As you can see here, it does a nice heat map and then shows you, okay, yeah, you're actually going to be having forces of up to 1.8. Oh goodness, I don't know what that unit is. Uris. I should have looked at the units before this, but you guys get the idea. Where they're worried about the ends of those, that where it gets red there, those forces getting too high. And so then you can redesign, add some thicknesses, add some different kind of constraints, maybe change the use case, which will change the amount of force that's going on it. All of those things are viable, but come from this finite element analysis. Next is 3D modeling for fluid dynamics. It's similar in principle to FEA, but instead of talking about the forces that are occurring, the stresses, I should say, throughout a part, this is showing what the aerodynamics of it look like when it's hit with a certain fluid flow. What's the response? And you can see it's very important in cars and in planes. How that's affected is absolutely critical. You'll also see it a lot in wind energy and how much energy there. What are the forces being generated on the blades based on the wind coming at it. On the right here, you can see some things that are set and then calculated. We certainly don't need to go into them, but you can see it gets really in depth. This is kind of what I was trying to show with this specific CAD software. And also similar to that is heat transfer. And this is very popular in HVAC settings, but also if you're an engineer designing parts that are going to be seeing a lot of heat, especially in electronic hardware, running those models is also incredibly helpful and being able to see, well, if you make some changes, what does the heat transfer differences actually look like? Where do the areas have to be worried about? I know one of my good friends who works in HVAC modeling. They take a model of what the school or hospital or museum looks like now, showing where their heat inefficiencies are, and then they just give a couple examples of what it looks like when they make a couple of changes, how those efficiencies change, and it makes it very visual for a client to see, but also quantitative. You can quantitatively then say how much in money, how much heat are you losing in a week, in a month, in a year. And it makes it for a much easier sales pitch, as opposed to just saying in general, yes, our service will save you money. Being able to see like this is absolutely huge. So I'm now super excited to show you guys what I made. You guys have been showing me so much of what you made, so I want to share some of my stuff now as well. I'll show you guys this in a second. This isn't it, as cool as that looks. Yeah, the sort windmill. So, as I mentioned to you guys, I work for the Museum of Science, and a part of that job is doing exhibit development work. So we are looking at an activity that we're calling sort. And the idea is the exhibit is this huge table with a trough of different sizing, color, and weighted balls at the top. And then the table is steel, and we give them different sorting tools and filters that have magnets on them. And then they use those magnets to sort by height, weight, size, material, all these different things to try to get each ball in its own bucket. And I designed a part just on paper for how to do weight. It was kind of like a fulcrum. And the idea was it had a spring on one side. I'm doing a bad job showing this, so that when a ball tipped it down, depending on how heavy that ball was coming down here, it would tip it more and change its trajectory. So if it was a heavy ball, it would kind of go down further, and if not, it would go farther away. Unfortunately, due to things that I'm not aware of and I'm learning for exhibits, springs are terrible to have in an exhibit because over a lot of use, springs really strain, and then they also have a tendency to snap off, which could really hurt someone. So it was replaced with a counterweight, which just moved a lot slower, and it wasn't working. So I've been really thinking a lot over the past couple of weeks about how do we solve this weight problem? How do we have people sort by weight in a way that's a little bit more effective? Because it would feel pretty bad if you're using what the exhibit supplies to do the thing you know you want to do, and it's not working. That's not fun at all, and for a museum, we need to do better than that. And I pitched this general idea to my manager, and this is one of the things I love CAD for. And in just using my words or drawing it on the whiteboard, it didn't really stick. It's entirely right. From what I communicated to her, it didn't sound that great. But she said, keep thinking on it, and we can come back to it. So I said, let me make a model. And I did. And when I showed her all of this, she was immediately like, this is awesome. I'm going to have you meet with one of the machine shop guys, and you can get moving. So this is something that we're going to go over in the next lecture, but essentially how I built this is in an assembly right now. Here I can bring the screen down a bit. You can see at the bottom here, I have each individual piece. So I made the fins that you can see that are on the sides, the disc at the top, and the central slide, and I put them together in assembly. And I did that because what you can do then is make it move. So I'm actually going to click on a part of it and hopefully it'll spin. Yeah. So this was able to show how this actually works. So if I can explain it to you guys, the idea is this is going to be, imagine the screen is the, just getting a back view here. The screen is the, oh goodness. The screen is the table. So these little holes are for magnets that are stick to the table, and a ball is going to come through. I wish I could just rotate this a little bit the way I want it. Yeah, here we go. Cool. So a ball would come through this way, and if it's light, great. It just keeps on going through. But if it's heavy, it'll be enough to tip this down, causing it to fall, bringing the next one into place. So the idea is if a ball's heavy, it'll drop down, then bring the next one over, let the balls roll through. And because I made this in a CAD software, not just drew it on the board, I could actually demonstrate how it works and how the pieces come together. And this will also help me, again, another use of CAD, this also helped me describe it to the machine shop guy and say, look, this is what I want. I was able to make it all with specifications. I could turn this into a 2D engineering kind of design layout if I wanted to, and get it made. It'd be not too hard. I'm thinking about doing just some CNC work. That's where you have a drill that kind of moves in a XYZ space to kind of chip away at different materials. It's great for woods and plastics. You can do it with metal too. You just need a much more powerful CNC than I'm going to have access to, which is just a tabletop CNC for right now, unless my friend in the machine shop wants to help me make it, which would be awesome. So I'll go over next week how I actually put all this together, because as I said, these are just individual parts that you can just insert. So I can say I want, give me another fin, but then it's just floating in 3D space. So the challenge then becomes how do you actually get them to cooperate and move all together, etc. So I'm going to cut this video for now and then start another one where I can show you guys my process of going through your assignment for this week.